Hi, my name is Haytham. I'm a master's student at Birzeit University, and I will present a paper titled Benchmarking and Performance Analysis for Distributed Cache Systems, a comparative case study. This work has been done with my colleagues Feras, Odeh, Rabee, Nasser, and my advisor Adel Taweel. Unfortunately, we are unable to attend the conference in person due to unforeseen circumstances related to visa. I'm happy to join you now virtually though, and we hope you all have a successful event. As we know, critical pieces of information that requires I/O-intensive queries or computationally intensive calculations are often cached in memory for faster access. Storing large amounts of data in a single memory, however, is expensive and sometimes infeasible. In addition, when we have distributed systems such as microservices, these systems likely need to store in and use data from a cache efficiently and reliably. Here, where distributed cache systems come. Distributed cache systems come to offer faster access by exploiting the memory of more than one machine, but appear as one logical big cache. Therefore, conducting performance analysis on these systems is necessary to study what and how factors such as number of clients and data sizes affect the performance. In this talk, as a roadmap, I'll start by introducing related work and some of research gaps briefly, which we endeavor to fill through this study, emerging the contributions and the goal of this paper. I'll show you the methodology we followed in this study as well as the experiment design. I'll walk you through the main contribution of this paper, including benchmarking algorithms, upon which we extend the yardstick framework as well as the results and findings of this study. Finally, I'll talk about the limitations of this study and conclude this talk by stating some key points and some work that can be done in the future. We can categorize related work into two types: benchmarks done by researchers in academia and benchmarks done by industry that offers distributed cache systems. Some studies analyze the performance of general distributed systems such as web application, cloud computing centers, or even general distributed software applications. A few studies, however, analyze the performance of distributed cache systems. As an example, Zhang et al. Analyzed the performance of three systems: Redis, Memcached, and Resilient Distributed Datasets (RDD). More recently, Das et al. Studied the performance for Hazelcast only. At the other extreme, notably, the majority of benchmarks are performed by industry, the vendors of distributed cache systems such as Hazelcast, Infinispan, and Apache Ignite, which may carry some bias in some cases. They usually publish their results either as white papers or on their websites. Examples on popular benchmarking frameworks include Yahoo Cloud Serving Benchmark and its extensions, RadarGun, and Yardstick Framework. Therefore, we can observe that most of the benchmarks are performed by their vendors. It's always a good idea to include benchmarks of these systems in scientific literature. Moreover, even though some have studied more than one factor such as number of client threads and targeted many types of cache operations, they studied multiple threads over one client connection. Little attention has been paid to study number of client connections, where each client opens its own connection to a distributed cache server, as well as the behavior when varying data sizes. For example, this case is prevalent in scalable microservices, where each microservice needs to open a client connection to the cache cluster. So in this study, we fill these gaps by 1. Introducing design space for controlled and an unbiased experiment to investigate the performance of distributed cache systems. 2. Extending yardstick framework, a general distributed systems framework to support important variables for benchmarking these systems. 3. Comparing between two popular open source systems, Hazelcast and Infinispan, focusing on retrieval operations only. Yardstick is an open source framework written in Java, and their authors allow the contributors to enhance and extend it. Mainly, we followed experimental research methodology to conduct this performance analysis study. First, we started by identifying the hypothesis. Then we listed all factors of interest. We controlled these factors, as we will see next, by specifying the conditions. Then we prepared the data that will be maintained by distributed cache systems. We prepared the experiment infrastructure, including client, server, and network. We built the benchmarks and ran them. After that, we analyzed the results, found out the patterns, and then reflected on the hypothesis. Okay, first, we start by formulating the hypothesis. This slide shows the null hypothesis, which we will reject later and accept the alternative, stating that there is an effect on performance measured by throughput of retrieval operations of distributed cache systems when varying the number of concurrent client connections and or the size of data maintained by the cache system. So, from the hypothesis, we are interested to study the performance of data retrieval operations. So, this is the dependent variable of interest. We measured this variable by computing the number of operations executed in a second, which represents the throughput. Regarding the factors that we controlled, they include, first, the number of concurrent clients. The conditions of this variable are 1, 2, 4 until we reach 128 clients, following 2 to the power x formula. The second independent variable is data size. We used 5 variations, starting from 100 records to 1 million records, following 10 to the power x formula. So we had data sizes of kilobyte and megabyte orders. Other variables that might affect the performance of data retrieval operations are related to environment, such as server and client machine specifications. Also, there are variables related to cache itself, such as the eviction policy, time to live, idle time, and so forth. All these factors were neutralized and made as much similar as possible for both systems. So here, we have some variables related to server and client machines. For example, we used Ubuntu 64-bit for both client and server machines. The RAM of server is 16 gigabytes, while the RAM of each client device is 8 gigabytes. Also, to enable networking between the clients and the server, we used network switch. It was Cisco Catalyst X series with 256 DRAM and 64 megabyte flash. As for the data that was stored in the distributed cache, we used the map data structure that contains a key and value. The value is an object of employee. The employee object has 5 attributes. 2 of them were set to be indexed, which are name and age attributes. It also contains an organization attribute. The organization object has 4 attributes. The name attribute was set to be indexed as well. So the relationship between employee and organization is basically many to one. So we prepared the data of different sizes as mentioned before using this schema. We chose 2 types of retrieval operations. The first type is a basic type, the get query. where you get one object by a key. The second type is more complex, the SQL-like type, where you can retrieve a collection of objects from cache. We formulated 4 SQL-like queries with different complexities. The complexity value is computed based on the number of logical and comparison operations. The higher the complexity value is, the greater the query's computation needs in terms of CPU and memory. The experiment setup included 5 machines and 1 switch for networking. 4 machines named host 1, 2, 3, and 4 were used to run client benchmarks, which generate the query requests. The distributed cache cluster was set up on the 5th machine named workstation. On the workstation, the distributed cache needs to be set up for each system. Each system would maintain data of sizes 100 to 1 million entries. Simply, for each cache system and for each data size, and after the cache is set up, the client benchmarks are invoked so that workstation can start receiving requests from clients. Now here's the algorithm that runs the client benchmarks. After the cache cluster is started up and run in a stable mode, the 4 hosts run the client benchmarks. Basically, for each number of concurrent client connections and for each query, the algorithm runs benchmarks concurrently, distributed over the 4 client hosts. So for example, for 64 clients and SQL-like 0, the algorithm would run 64 benchmarks concurrently on the 4 hosts. Thus, each host would have 16 benchmarks. The running algorithms along with benchmarks logic were implemented upon yardstick in Java language, as well as using shell scripts for controlling the runs. The project of this experiment can be found on this GitHub repository. The design of the whole experiments was developed over many iterations of dry runs and trials. To ensure high fidelity of our experiments, CPU memory utilization was monitored to make sure that the resources of machines were not exhausted. Okay, so now let's see the results and findings. For all next charts, the x-axis represents the number of clients, while the y-axis represents the throughput, which is the number of operations per second. The color of a curve indicates a data size, and it's displayed only where necessary. For getToQuery, we see that Infinispan scales better than Hazelcast as number of concurrent client connections increases. The throughput of Hazelcast dropped down when moving from 64 clients to 128 clients. We can notice also when increasing data size from 100 to 1 million entries, the behavior almost the same. That's why the curves are close to each other. The throughput of Hazelcast, however, drops down by around 19% on average. For the first SQL-like query, which is SQL-like 0 query, The throughput of both systems is significantly small compared to what the case is in get a query. There is a significant drop when varying the data size for both systems. The effect of concurrent client connections becomes less significant on larger data sizes for both systems. We also notice that Hazelcast outperforms Infinispan for 100 data size by 58%. However, Infinispan outperforms for all bigger data sizes as shown here. The results of SQL-like one query are almost same. Hazelcast outperforms Infinispan for 100 data size only by 40%. Infinispan outperforms for all bigger data sizes too. The results of SQL-like 2 query are the same as well. Hazelcast outperforms Infinispan for 100 data size only by 56%. Infinispan outperforms all bigger data sizes. Also, the results of SQL-like 3 query are very similar to previous ones. Hazelcast, however, this time outperforms Infinispan for 100 and 1000 data sizes. Infinispan, however, outperforms for all bigger data sizes. That difference in performance between Infinispan and Hazelcast is due to, first, data serialization. Hazelcast uses default Java implementation for serialization and deserialization, which is slow and produces unnecessarily large bytes, whereas Infinispan uses JPOS marshalling framework, which is considered very powerful. Second, in-memory object formats. In Hazelcast, the default format is binary format, which is not efficient if the application is doing a lot of SQL-like queries. This explains the bad performance of Hazelcast on SQL-like queries, especially for large data sizes. Third, indexing. Even though indexing was enabled for both systems, the engine of Infinispan is built upon Hibernate Search and Apache Lucene, which are considered more optimized than Hazelcast's default one. This study has some limitations where they could be considered in future work. First, the scope of this study focused on retrieval operations only, and did not take into account the other operations such as put and set. Second, a linear approximation was used between number of clients. So, for example, the behavior between 64 and 128 was not persuasive enough due to large difference. Third, the data sizes that were used in this experiment are order of megabytes, which might be rather small in some cases. However, we noticed that varying data size really affects the performance. So generally, this study reveals the behavior of throughput of distributed cache systems as a function of concurrent client connections and data size. We can now revisit the hypothesis and support the claim stating that changing the number of concurrent clients and varying process data sizes affect the performance of data retrieval operations of distributed cache systems. We have seen that results show that Infinispan outperforms Hazelcast in most cases except in SQL-like queries for small data sizes. We have found that the throughput of SQL-like queries is more sensitive to data sizes than to client connections, whereas getQuery is more sensitive to concurrent connections than to data sizes. As a future work, a more thorough study can be done to consider other interesting factors such as data storage formats, larger data sizes, cache access patterns and modes, and communication protocols. Also, it might be interesting to community to develop new techniques of data representation and communication protocols for improving performance of such systems. Finally, this study promotes building extending benchmarking tools that produces metrics as a function of different factors like concurrent client connection and data size, not only as a function of time, which is prevalent in most benchmarking frameworks. I hope you enjoyed this talk. Please do not hesitate to forward me any question feedback to my email at salhi9899@gmail.com. We will be happy to answer any questions. Thank you.